Hi everyone, we're just going to get started. This is workshop 5, an introduction to deep learning. So before I get started, can all of you please scan this attendance QR code so we can keep your attendance. Thank you very much. Hey.
Hello.
You're just in time, we're just getting started. Please make sure to scan the QR code so we can take down your attendance. Thank you. Hello.
Hello. You're just coming in, make sure to scan the QR code for it to be attended. Thank you.
Few minutes for people to register for attendance. I think we can get started. So first of all, announcements. But there's only one announcement. Milestone 4 is due tonight at 11:59 p.m. The submission link is on the DSGT Bootcamp website. As always, if you have any questions on that, feel free to stay afterwards the lecture. Okay, so what is deep learning? So deep learning is this new approach to machine learning in a way that tries to automate as much as possible. So deep learning is a more deeper layer of machine learning. Machine learning still involves some aspects of human control. For example, in defining the features of an object, for example, a picture or something else, there is still some element of human intervention. But in deep learning, we are trying to automate that as much as possible. For things like feature extraction, we're trying to give it all to the neural network to solve. So, deep learning. So before we get started on what is computerized neural networks, let's start talking about the inspiration from where we get neural networks. Let's talk about real neural networks, or specifically the neurons that exist within our brain, spinal cords, and all of our body. So how does a neuron send signals across the body? In this picture, which I stole from the YouTube page Veritasium, which I highly encourage you to watch his video. It's very formative about deep learning and machine learning. So here we see 5 input neurons and one output neuron. Each neuron can either be activated or not activated. In simple terms, that can be a binary representation of 0 for not activated or 1 for activated. Each of these neurons will send their signal, whether it's activated or not, into a final destination neuron. And each of these signals can have its own activation weights. It can be a positive weight or a negative weight. And what this final neuron will do is that it will perform a very simple matrix dot multiplication. So here we see the output being equal to 1 multiplied by 5. So 1 multiplied by 5 plus 1 multiplied by -2 plus 0 multiplied by 1 plus 1 multiplied by 6 plus 0 times -7. And when we do that math, we arrive to an answer. So in this case, it will be 9. And when it gets that output, it will try to compare that output with a certain threshold value. So for example, 4. If the output is more than 4, we activate 1. If it's not higher than 4, it is not activated, 0. So that is how a real-life neural network works. But when we get into computerized neural networks, we try to simplify things a bit and try to give more information in as little neurons as possible. So specifically, for example, when we are turning an image into a bunch of pixels, those pixels can either be 0 or 1, but for compacting more information into smaller amounts of space, we now give it a float value between 0 and 1. So it can be 0, 0.1, 0.9, and values up to 1. And then we tie it all together, all of these pixel values or block values of the picture into one neuron. And the same as the real neural network example, it will perform a matrix dot multiplication. So 0.5 multiplied by -3, 0.5 times 6, and then you add them all up and you arrive to a float value, for example, 0.4, and then using that and determine whether that float value is the one that you output or the one that you will share to the upcoming neural layers. And another distinction that we make in computerizing our neural networks is this thing called the bias. So the bias is essentially an input of 1, exactly 1, and we only change the bias value or the weight of this bias link in order to change the output. This is very useful if we want to change the output without changing the weights or the inputs of the other inputs. So here, y is equal to wx plus b multiplied by 1. So y is the output, x is the input, w is the weight that we give to that input x, and b is the bias value. And here plus, that just means a linear function. So a linear function is simply, y is equal to mx plus b. You're just changing the gradient in the output graph, for example. And moving on, what is a dense layer? So a dense layer simply means that all of the layers within that neural layer, all of the neurons within that layer is connected to every other neuron in the previous layer. So if you can see here, all of the neurons in the second layer is connected to every neuron in the first layer, and therefore layer 2 is itself a dense layer. And when we have all of the layers, we have what we call a dense neural network. Okay, so linear unit. So taking slides from this source, which I also encourage you to see for yourself. So what if we have a normal linear function as our activation unit, as the unit that processes the output from its given inputs? Well, what we have is a single gradient, a single line with an ever-changing gradient. So it will work in cases like this. So putting all of these values, blue for cats and red for dogs, you will want your machine to learn the difference between these images, and when the difference between those two animals are distinct and you can plot them in a straight, clean cut, then you will arrive to a successful distinction between the pictures of the dog and the pictures of the cat. However, it does get complicated and unrealistic as we move into more and more real life or other objects. So in this case, a nice, clean, straight line will not work anymore. So what we need is something not linear, something that is more curvy, something that will fit into the patterns of the picture that we want to distinguish from. So what we need is what we call an activation function, or in very simple terms, a non-linear function. So we're not just looking into y is equal to mx plus b. We are looking, for example, into a sigmoid curve or a tangent curve or a sine curve. That way we can really bend the curve to suit our distinction. And in this case, we are getting a parabolic curve, and the parabolic works to separate the pictures of the dog and the cat. So that is an activation function, just a nonlinear function. And it's a nonlinear function that we put to produce the output from its given inputs. It turns out there is one activation function that tends to work very well with a lot of our machine learning requirements, and that is what we call the rectifier function. So what is the rectifier function? So the rectifier function is really an extremely simple function. It is a function that rectifies the output to 0 whenever the input is less than 0. So here in this case, we see that in all cases where the input is between 0 and 1, that will be its exact output. But whenever the input is less than 0, whenever the input is negative, we will force the output to be 0. That is what we call a rectifier function. So it tends to work very well with a lot of our models, and whenever you are curious as to which activation function to use, the rectifier function is a very good candidate to start from. And when we combine a rectifier function into a linear function, we get what we call a rectified linear unit. So rectified linear unit, or ReLU, which is commonly called a ReLU function. So applying a ReLU activation function to a linear unit will just force the output to be y is equal to, so instead of y is equal to mx plus b, adding the linear rectifier function will just force the output to be maximum between 0 mx plus b. So it's either mx plus b or 0, whichever is more. And in order to declare whether what activation function you want to use whenever you are creating a neural network using keras of tensor overflow, you will just declare, for example, layers.activation ReLU. Oh, and I really forgot. How do you declare a neural layer in keras, which is a part of the TensorFlow library? So in order for you to do that, you just import these two stuff, and you declare a keras.sequential, and you input the list of all of the layers that you want. So here we have only one layer of neural network, and the number of neurons within this layer is 1, and there are 3 inputs that are going into this neural layer. So here, that is essentially just 3 inputs going into one neuron and outputting the output. So that is what this formula is representing. If you want to add more layers, you just add more stuff into the list. So layers dot then stuff. Oops. Okay. And moving on. So obviously there are other alternatives to ReLU, for example, ELU, SELU, or Swish, among others. But whenever you are not sure of which activation function to use specifically, ReLU is a very good place to start with. Now, stacking dense layers, you might have heard that in order to make your neural network work much more efficiently and much more accurately, you need to add more and more layers to this neural network. And what that means is just that all of the inputs from the previous layer will just feed into the next layer and the next layer and so on until it hopefully arrives to a more accurate solution which you are looking for. And this, like I said, is how you build more deeper sequential models. So in order for you to add more layers, you just add more, you just append new layers into this keras.sequential list. And here we have a typical neural layer. So this is 4 layers of neural layers, each with 512 neurons, each using the ReLU activation function, and the first one having an input number of 11 objects. And also one thing to mention, the last neural layer may or may not be a rectifier activation function. And the reason why we don't want to put a ReLU activation function at the very end of the neural layer is because, as the definition of the ReLU function, the output must be at least 0. So if we want to get a negative number as the output, using the rectifier function as the final layer will just not work. So in this case, we will want to use a linear network. But again, it really depends on what are you looking for. Are you looking for a regression or a classification or something else? And next, the loss function. So now we have understood how to design the architecture of the neural network. Now, how do we compute its difference? How do we compute how accurate the system is? And here we arrive to what we call the loss function. So loss function is just this field of machine learning in computing how accurate your solution is. And one of the easiest and most efficient, most used way to compute your accuracy is just to measure the difference of your output versus your expected output and just adding them all up. So here, for example, we have this straight line being your real output and the many dots representing the expected outputs. So in order for you to calculate the loss of your machine in classifying your images, you will just add all of the differences between all of the y-axis between those dots and the linear line. So it will be this y function. It will be just y value plus this y value plus this y value plus this y value, and so on and so forth. And then you get an MAE of 0.993 in this example. Obviously, there are other ways. For example, you can compute the squares of those, the mean square values of those differences, or using the what we call the Huber loss function. But really there are many ways, and the MAE is one of the ways that you can start, in one of the most complex and efficient ways for you to understand your loss. Right? Any questions up to now? Okay, awesome. I'll just give the floor to my colleague Abhijat to continue the rest.
All right, let me share my screen.
Go ahead.
Perfect. All right, so this was definitely a lot of material, right? So I'll be picking up from there. So the loss function is really important because this is how you want to train or retrain the model and update the weight so that the accuracy can go up. There will be less noise, and the neural net can perform better. Now, how does it go about doing that? Well, it uses an algorithm known as stochastic gradient descent. What is stochastic gradient descent? I have a presentation to tell you about it. So let's talk about gradient descent first. Gradient descent is basically an algorithm that is used to incrementally incrementally update the state until you converge at a minimum or at an extremum. What this means is, so let's say you have, let's say you have like a curve, right? And the curve represents the amount of error that you're going to have. What your goal is to minimize that error so that the algorithm can perform at its optimum. And it uses the change or the slope at a particular point, and which is the state, and it goes and ideally it goes down a step size further, and then it keeps on going until it reaches and it converges to a minimum point or a local minimum specifically. So that's what gradient descent is. Gradient is just a way of, so like if some of you have taken like multivariable, or I don't know if linear algebra, I don't remember if linear algebra touches upon this as much. I know multivariable does, but the gradient is essentially, a fastest way to climb up or down a curve. And there's like a whole like proof on that, but which I'm not going to get to because, yeah. But basically, the gradient, so in an xy curve, there's a change in x and a change in y, also known as the derivative. The vector that takes those derivatives is the gradient. And that gradient is a way of saying what direction is the fastest that it can climb up or go down. So that's what gradient is, and we use that to for basically all of our gradient descent algorithms because then it gives more of a real what sort of errors that we're dealing with. So now the mechanics of it. So as I said, in the curve, like a 3D surface or something, you have multiple axes, x, y, and z along a surface S. And the change is, within that function, you calculate the partial derivatives, which is the derivative of x with respect to the derivative of the function with respect to an individual variable. So you can have a partial for x, partial for y, and partial for z, and that vector will take those partial derivatives into a gradient. So that's the mechanics of it. So now that you have the gradient, you want to use that in gradient descent. Like how you take those values and you plug it into basically the gradient descent algorithm. So you calculate the gradient and you use the step size. So there's a whole formula with that, which I'll go to the next page. So here you have the previous state, you have the step size as gamma, you have the gradient, and you multiply it by the previous state, and that will give you the next state. I thought I had a picture. Oh, yeah, I do. So here, what this means is, so the step size can be any number. That is something that you actually hypertune and do like experimentation on. But let's say that this white dot is let's say that this dot right here is the current state that you're trying to calculate, right? So this white dot is a previous state. And then the difference along the curve is what gradient descent is trying to calculate. So once it has it, so it takes in a step size, it takes a gradient, it does the computation, and then the final values of the state will be in this dot right here. And it'll keep them going until it reaches to the bottom, to the local minimum. Now, notice that it's not really the correct minimum. And this is where stochastic gradient descent comes in. Stochastic gradient descent is an extension of gradient descent in which you're randomly choosing a start state or a start point on the curve. So in this graph, you could randomly choose a point here, or you could randomly choose a point here, and then it will take in the minimum set that are calculated from the gradient descent implementations, and then it will show the minimum error. So this is how it works. And that's gradient descent. So now let's get back to why is this important? Well, stochastic gradient descent is, as I said, it's important for optimizing your deep learning algorithm. And the algorithm is iterative. So it iteratively samples some training data and runs it through a network to make predictions. And then so it goes through forward propagation, and it uses the weights like what Faris was talking about, and the activation functions, and it outputs a value. And then based on the training labels or training values, it calculates a loss, and then it uses back propagation to adjust the weights to minimize that loss. And that's what this diagram is showing here. Here you have the points, and you're trying to fit a line. Here is showing the training loss as it continually tries to decrease. And here are the curves showing that they're supposed to be approaching these ideal weights. And ultimately, like after you run it iteratively, it will start to approach those weights and get to a proper answer. All right. So to introduce some more terminology, I talked to you about the learning rate. That is So the learning rate is basically the step size that I showed you. You want learning, so it's a hyperparameter, which means you have to normally when you're running these sort of optimization algorithms, the learning rate is a very important hyperparameter that can basically determine how well it's going to perform. And it takes a lot of experimentation. You could have a learning rate that is very narrow, in which case it has to go through so many batches of data. And so that's another terminology. Like the batch size is the amount of the number of data points that you're trying to sample each time you run through a gradient descent algorithm. And the learning rate, so the smaller the learning rate, the more of those mini batches you're going to have to run, and therefore the more iterations. And the same thing, vice versa. So once you have those things, so the learning rate and the size of mini batches are the two parameters that will give the largest effect on the stochastic gradient descent algorithm. So now now that you have the loss function and you have the optimizer, which is the SGD algorithm, you run it through this code right here. So here you have optimizer, which is Atom, and Atom just is just the name for the optimization function, and the loss can be mean absolute error, mean squared error, or any one that you choose based on it really depends on the problem. But for this case, we'll just say where the loss is the mean absolute error. So that's how you add the loss in the optimizer to the model. Now, I'm going to run through some examples. So here with this code, you're reading through a CSV for a red line, and you're trying to output the quality of it. So here here you create the training and validation splits by using a 70 and 30% split, and then you're displaying, and then here you're just displaying the top four rows of the data frame. So then let me just make sure it runs properly. Okay, good. So here is interesting. So this is where you start to standardize and make changes to the data frame such that it will make the algorithm it will make it easier for the algorithm to perform its computations. And I'll talk about that later. But here you just have to know that it scales it based on the minimum for each column. And then what this does is that it splits training and validation, and that's how it. So the reason why you want to have training and validation. So training, the training data set is where you're actually training the model. Validation is where you're using the loss and optimization function and you're updating the weight. So you want to have both. Here you can just get the size of the data frame, so the number of rows and number of columns. at indices 0 and 1 respectively. And then here, as Faris has already stated, is the typical implementation of a neural network. So what this is saying is you have an input chip of 11, and in the density you have 512 nodes, and then your activation is ReLU. And then you have another hidden layer with 512, and another hidden layer, and then you have the output layer. So the output layer is always the last element in the list of the array that you're putting in as a parameter for the KRS.sequential. Now, notice that we have 11 input layers, right? So this corresponds to the 11 inputs or the 11 columns in the data frame itself, which is what I want you guys to pay attention to. As you can see here, so these are the 11 columns, and each of them has like its own, list of values that in each data point. So they're going to have different weights. They're going to have like different sort of importance to the model. So like let's say that in order to determine the quality of red wine, this feature is not as important, but this one is. I'm just saying, like, I'm just giving an example. Like, you want each of those to be its separate input node with its weight. And this will end up having a lower weight, and this will end up having a higher weight. And that way, this will have a higher case in determining the quality of red wine. So that's what I'm talking about with, like, mapping the columns or like how the data frame is to the actual neural network itself. So that is something that you need to keep in mind. And then, of course, here you add the optimizer, as I've said before, and the loss as well. And now we're ready to fit the model. So some terminology, I know. So remember what I told you about batch size? That is the number of samples that number of data points you're trying to sample each time each implementation, and the total round of all the data is known as an epoch, or I actually don't know how to pronounce it, so sorry about that. And here, so then here what you're doing is you're taking that batch size to be 256. That is a sort of common starting value when you're fitting the model. And here you're running it in 10 epochs, which is 10 iterations of all the samples, or mini batches rather. So you run this, and as you can see, oh, what happened? Okay. And then this one is not doing it. I didn't run this. Okay, there we go. Sorry about that. So as you can see, it's for each time it iterates through like an epoch, it calculates the loss, and then it updates the weights, and then the loss just keeps going down and down and down. So by the time you reach the last epoch, the loss will be at 0.1015, and the validation loss will keep on going down. So both of those things show that the more and more you train the model, like you could have it run 12 of those, and then that way, so then it went down even more. So that's how it just continually updates the weights. It minimizes the loss, and it uses the stochastic gradient descent for optimization. To visualize this, you can to visualize this, right? Notice that we have loss and we have validation loss from when we actually ran the model.fit function. And this is going to show that as the loss reduces, the validation loss also goes down, and it does so when you run more and more iterations. So that's what this is. All right, so now let's talk about overfitting and underfitting. Now, we probably have talked about overfitting and underfitting many times in previous workshops, and the reason for that is it's just a very sort of universal thing to think about when doing machine learning or deep learning in general. So can anyone just do a recap on what overfitting and underfitting is? Anybody? Go ahead.
Overfitting is when the model fits tightly to the data and then catches.
Yeah, exactly. So so you're exactly right. Overfitting is when you're trying to capture all the data points or all the noise, and the function ends up being way too complex that it ends up being easily changed when one point is taken off, or when when another point is added in, and things like that. So with that complex a model, your training accuracy can be pretty high, but your testing accuracy can be quite low. So that's overfitting. Underfitting is the opposite. Underfitting is when your model is not complex enough. So what you want to get is somewhere in between. So this applies to deep learning as well. One of the things about deep learning and neural nets is you're not only using like nonlinear. You not only have to consider the activation function that you're using, like ReLU or like any other nonlinear function, right? You also have to consider how many units in a dense layer, how many of those dense layers you want to have, and of course the input and the output. So if your neural network is too complex, it will lead to overfitting. And when that happens, you want to have you want to start considering dropping some of the nodes to prevent this overfitting from happening. And that's where the dropout layer comes in. The dropout layer is it's just a way in which, so for each dense layer, you have some nodes that are considered and some nodes that are not considered. So here, the dropout percentage is 50%. So it's out of these four units, or these four nodes, only two of those are being considered. And that can be pretty helpful because that means that, like, of course you can test and see which of the nodes because then you're running like mini groups of, multiple groups of a smaller group of nodes instead of just having to run all of them at once. So you will get better results without losing any data, and to prevent overfitting, which is what dropout, which is a function of dropout. And a way to add a dropout is you just do layer.dropout, and the rate, you set it to the percentage. So here we set it to 0.3, which means that 30% of the nodes will be dropped out in consideration. Any sort of group of nodes that are considered, and there will be multiple of those, and any group of nodes considered will have 70% of those nodes. So that's what it is. Now, the next part for improving or simplifying the computations and preventing like unpredictable behavior from in deep learning is batch normalization. Now, remember when I talked about how we, like, if you go up further at the top, when we actually split the data, we scaled it to be between 0 and 1. So this happens, so this is one way of standardizing or normalizing the inputs, right? So this normalizes it based on the max and min, and it does it before it even goes gets trained in the model. So that is one way you can standardize it. With batch normalization, you can basically standardize it any time during when the algorithm is being run. So so let's say that you have a value like 100 and a value of 1, right? Like, so those are two inputs, and and you have different weights for each of those. Now, if you find the result with an activation function like ReLU, it's going to lead to unstable behavior, and it's going to lead to like weights being skewed, too high or too low, and it'll just lead to like unstable behavior. So which will end up skewing the output also. So to prevent that, you normalize the batches, and so a way in which you can do that is some ways you can do that is you can normalize the batches through through different statistics like mean and standard deviation. You could also take all those batches and just normalize it by the min and max. You could do so many things. And what this will do is it will have it in a sort of scale, which will be easier for the algorithm to calculate consistent weights and output a value. So a way to add batch normalization is you just call the method right here. So you could either do it after a layer or after a dense layer. You could do it between a layer and its activating function here. So like the difference is you're just calling the activation function earlier here than you are here. And of course, so it just presents you like with different options on when you want to normalize your samples or your nodes, and that's where you guys can play around with that. So this is just a common implementation on that includes all of it. So here you have a dense layer of 1024 with input shape of 11 nodes. You're dropping out. You have a dropout layer of 30% for that particular dense layer. Then you normalize that batch in that layer, and then you go to the next one. You do the same thing. Then you go to the next one. You do the same thing, and then finally you have the output layer. And then of course, once all is said and done, you add the optimizer and the loss function. You fit it with the batch size and the number of epochs, and then this will just put in the data frame and in the matplotlib graph. And that is all. That is all that there is to neural networks, deep learning, and machine learning in general. Thank you all for coming along with this with these workshops. And I know this information can be tough to grasp, but it really is a lot of fun. Like like experimenting and finding ways which will work best for like a particular problem. So yeah, do you guys have any questions? Go ahead.
How do you decide on the number of nodes in a layer and the number of dense layers to use in the network?
Yeah, see, so that's a good question. So you remember that in the dense layer we had like 256 or 512 was in the dense layer. That is normally a common number that people put into star, and so it's just a typical way of doing it. There's a Stack Overflow post that I can share with you guys after the workshop, but basically some things that you want to consider is complexity, number of inputs, of course, and whether you want it to be a classification or a regression problem. So all of those things come into play here, and of course, there's not really like one way of determining how many dense layers you want or how many input layers how many nodes or units you want in each dense layer. It's just a matter of experimenting. It's a good question.
So, do you suggest using dropout every time by default?
So dropout, the main sort of purpose of the dropout layer is to prevent a model from overfitting. So there will be chances where your model is too complex or you have too many nodes in your dense layer that needed for a problem. So you want to drop, if you want to drop, like 60%, then you basically just disregard the 60% of the nodes. And I'm not sure exactly how the implementation actually goes. I'm sure that there's a bit of randomization with that, and it just divides them into like different groups, different combinations of those nodes. So so with dropout, it's able to calculate the weights, or no, not the weights. It's able to use the weights and calculate the values for the next dense layer or for the output node, and it does it for each group of 4 candidates, for example. So that's sort of what dropout is. If you want like more intuition, I'm sure that there's some documentation in Keras or in like TensorFlow. So I haven't looked at it myself much, but if you want to go dropout, you can check it out. Yep, no problem. Anyone else have any questions? All right, well, if no one else has any questions, I think we should.
So thank you everyone for coming. This is the last workshop for the DSGT Bootcamp of this semester. Thank you all for coming. Milestone 4 is due tonight, so let us know if you have any questions on that. And before you all go, please just make sure that you all have scanned this QR code so we can record your attendance. But other than that, thank you very much, and you're free to go.
Thanks for coming, y'all.